Hey everybody, welcome back to physics. We're going to keep talking about what waves do in the universe. Today we're going to learn how to break a wine glass with your voice. That's the first thing we're going to talk about. So let's start with a YouTube video inside of a YouTube video. I want you to watch closely of what this guy does in order to break the wine glass with his voice. Watch carefully. Look at this cool guy. Loading. All right, so watch all the steps that he takes in order to break this wine glass with his voice. Listen to the volume of his voice. Watch every step that he takes in order to break the glass. Look at that straw going. Look how excited he is. All right. So before we watch it one more time, notice what he does. He flicks the glass and he listens closely. And then he creates this tone with his voice. I think common knowledge is that you just scream at a piece of glass enough, that glass will break. But there's something very particular you have to do in order to break the glass. Listen to what he does and listen closely to the sounds of his voice and the sound that the glass makes when he flicks it. So what he's doing, he's listening to the tone that the glass creates when he flicks at it, and then he creates that same tone with his voice. This has less to do with the volume of his voice and more to do with him matching the tone that the wine glass is creating. And what he is showing us is an example of this idea of resonance. Resonance is defined as a forced vibration in an object due to an applied frequency that matches the natural frequency of the object. So when he flicked the wine glass, that tone that the wine glass created was the natural frequency of the wine glass. You could flick a lot of different things. You could catch the natural frequency of any kind of object around you if you flick it and listen closely to the pitch that it creates. And then if you match the frequency to the natural frequency, he's creating it with his voice. We know that our voice is a longitudinal wave, that mechanical wave shaking the air, and then the air shakes the wine glass at just the right frequency. When the applied frequency matches the natural frequency, the amplitude of the resulting wave increases. This is how instruments increase the volume of their music, and a destructive example is how we shatter a wine glass. So what's happening is you flick the wine glass, it vibrates, and you could hear the frequency it vibrates at. But when we create that tone with our voice, we're pushing the wine glass just the right way, at just the right time to increase the wave. There's actually a wave going on inside the wine glass, and that amplitude of that wave increases because of the frequency that we're creating with our voice. A really good example of resonance is pushing a kid on a swing. Now, if we push that kid at any random intervals, we wouldn't be able to gain any height on the swing. But if we push the kid at just the right intervals, when it's back towards us, matching the natural frequency of the swing, we can create a higher amplitude of the swing. That would be an example of resonance. Another cool thing you could do, I'm not sure if you've ever seen tuning forks before, but tuning forks are built to vibrate at certain frequencies. You could have a tuning fork creating the note E, let's say, and you strike the tuning fork and it'll vibrate the air at the note E. But if I have two tuning forks right next to each other, both built to play like an E note, and we flick one, the other one will start to vibrate even though the only thing connecting these two is the air surrounding them. That's because as this tuning fork vibrates, it'll vibrate the air at the note of E, and then that note will hit the tuning fork at the natural frequency of the tuning fork, and then the tuning fork will start to vibrate at that E frequency. Then we could stop this vibration and start to hear the vibration from the other tuning fork. This is an example of resonance. A lot of instruments are built in order to resonate at certain frequencies to increase the volume, the amplitude of the note that it's creating, or there's different notes it's creating. And another more destructive example of resonance actually comes from a bridge in the 1940s. There was this bridge that was called the Tacoma Narrows Bridge. Now this bridge is a suspension bridge. I'll put a video in our post, but the Tacoma Narrows Bridge was a big bridge that was built in the 40s, and it was built in such a way. So it was built, it worked for a few months, but even while they were building it, the engineers kind of noticed that the thing rocked a lot. They nicknamed it the Galloping Gertie. So they built this bridge, and this bridge was known to vibrate a lot in the wind. And then one day in the 40s, the wind passing over the bridge actually ended up playing this bridge like an instrument. And this bridge started vibrating, and the amplitude of the vibrations increased because the air resonated the bridge. And it's pretty wild to see the video because the bridge just looked like a ribbon connecting the two land masses. And eventually the bridge vibrated so much that it collapsed. This is also why soldiers, when they cross a bridge, soldiers are known to march in unison, but when they cross a bridge, they make sure that they march out of unison to avoid any kind of resonance effects on the bridge. So resonance is something that waves can do. We could travel this frequency across the air and cause other things to vibrate and increase their frequency through this idea of resonance. Okay. So the next thing I want to do is I kind of want to just review this idea of interference a bit more before we move on to the next topics. We saw interference a bit already, but something else that waves can do is they can interfere with one another. Now, waves are not objects. We're transmitting energy through the universe. Objects cannot occupy the same space at the same time, but waves can occupy the same space at the same time. And that's principle is called superposition. Superposition, just meaning that they can occupy the same space at the same time. So what does that mean? What happens when waves occupy the same space at the same time? Well, because waves transmit energy, and energy can neither be created nor destroyed, that energy has to be manifested somehow on the wave if they could overlap one another. And we get this interference pattern. Watch these waves as they pass one another. When they pass over, we have areas of constructive interference where we get a greater amplitude, and we have areas of destructive interference where we get a lesser amplitude. Superposition, the best way to think about it is it's just the algebraic sum of the individual disturbances. Algebraic sum means we're just taking note of positive and negative numbers. If we have two crests, we're going to have a greater amplitude, just like adding two positive numbers. And if we have a crest and a trough, we'll have a smaller amplitude, just like adding a positive and a negative number. Because that energy can't disappear. It still has to be manifested somehow on this wave. Okay, so here's an example of constructive interference, another vocabulary word in waves. It's a lot of words we have to keep track of here. Constructive interference is just like it sounds, constructing. The waves end up with a higher amplitude when we have constructive interference. Notice these two crests come together, and when they overlap, when these waves interfere, occupying the same space, we end up with a higher amplitude wave. And then those two wave pulses move right through one another. Objects, when they hit, they collide and they bounce. But waves, because they occupy the same space, they move right through one another. You have wave pulse A moving in, wave pulse B moving through, and then those pulses pass right through one another. This principle can be seen with troughs as well. Let's say we have a trough coming in and a trough coming in. Now, because they're facing the same direction, we're going to end up with constructive interference. We have A, B, A plus B, and then those two troughs will pass through one another. They're not bouncing off, they're passing through. Here's A, and here's B. Okay, so that's constructive interference. Now, you might have guessed it, there's also destructive interference. And when we have destructive interference, the two waves add together and the resultant disturbance is lesser in amplitude than either of the individual disturbances. So here's two examples here. We have a crest moving in, we have a trough moving in. And then when they occupy the same space, the dotted lines are what the pulses would look like. But we actually end up with just a straight line. This energy's upwards, this energy's downwards. So you end up with perfectly destructive interference here. And then each pulse moves away from one another. This proves that these wave pulses are not bouncing off one another, but they're moving through. If they bounced off, then we would see this crest moving in this direction, but they're moving through. So the crest moves past that area where they overlap, and the trough moves past the area they overlap. Now here's an example where the amplitudes don't match. Here we have, let's say, like a +1 and a -1 amplitude. Here we have like a +2 and a -1. When they interfere, the resulting disturbance is less in amplitude, has a lesser amplitude than either of the individual disturbances. They interfere, we end up with a small little bump, and then they move right through one another. That's destructive interference. Another example of interference that we can observe in nature is this idea of beats. My musicians here, they might recognize this idea of beats. You might have discussed in your music classes. But if you're tuning your instrument, let's say you're tuning it based on a reference sound. We're trying to get to like 100 hertz frequency, like that's the sound of the wave. Hertz is the pitch of the wave. We're trying to get to 100 hertz, but we're still a little bit off. We're creating a frequency of 110 hertz. They look almost similar, but because they're a little off and not quite repeating at the same intervals, you actually end up with these areas of constructive interference and these areas of destructive interference. Now, what does this mean for sound? Well, we know the amplitude of the sound has to do with the loudness of the sound. So the areas where we have high constructive interference, we're going to hear a louder sound. And areas of destructive interference, we're going to hear a quieter sound. This is something you could clearly create with speakers. With two speakers, you actually create places where you actually hear no sound at all. So as we play this out, as we get closer and closer to the note that we want to tune to, what you start hearing is wah, 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 wah. You actually hear the areas of high sound and the areas of low sound. And then as we get closer and closer to the actual frequency, the beat frequency decreases. So you'll start hearing wah, 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 wah. And then eventually when it matches perfectly, you won't hear any beats at all. The reason why you hear those beats has to do with this idea of interference. The waves interfering with one another, occupying the same space, and you get areas of constructive interference and areas of destructive interference. Okay, so let's try some interference examples here. We're just going to go through these two real quick. Here on the left, we have a diagram below showing two pulses approaching each other in a uniform medium. We have a 5 centimeter pulse and a 10 centimeter pulse. Which diagram best represents the superposition of the two pulses? Superposition is telling us that they're occupying the same space at the same time. Is it 7.5 centimeters, 5 centimeters, 15 centimeters, or is it 5 centimeters downwards? Well, if we said that the superposition is the algebraic sum of the two pulses, we have a 5 centimeter pulse here, 10 centimeter pulse here. They're both upwards, so they're both like positive numbers in these cases. The correct answer is choice 2, 15 centimeters. Now this one's interesting. We have a square wave heading in, and then we have a rounded wave moving in. It's actually possible to have square waves. Square waves are apparent in things like binary transmission of information, where you could have things on or off. Here would be on, here would be off. So we have a square wave moving in, we have a rounded wave moving in. What happens when the two pulses meet at point X? Well, we know it's the algebraic sum of the two pulses. So if the square wave was here, it would look like this. And then if this pulse was here, it would look rounded. So the square pulse goes vertically up, so we already end up at this point. But the rounded one takes some time to get up to that amplitude. So there's nothing on the rounded pulse here, but we have maximum on the square pulse. So if we were to overlay these two, it would look something like this. Because the lower pulse is taking away, but at this initial point here, we still have that tall aspect of the square wave. The correct answer here is choice 4. The rounded wave takes away, has maximum destructive interference at that center point, but otherwise it doesn't take away as much from the amplitude of the square wave. So next, I want to look at a really particular example of interference. Something when the two waves match in some really interesting ways. So let's say we're sending two waves in towards one another, and they interfere with one another. And we have two waves interfering, and they have equal frequency, amplitude, and wavelength, traveling in opposite directions. We get something called a standing wave. What a standing wave is, the resulting disturbance of these two waves passing over one another, interfering, occupying the same space, we get a resulting disturbance that looks like it's stationary in space. That's where the term standing wave comes from. Notice this resulting disturbance here. We have areas where the wave oscillates up and down, and we have areas where the wave stays stationary. Now keep in mind, this is a manifestation of two waves moving through space that are interfering, creating this pattern. They have to have equal frequency, amplitude, and wavelength. If you have a slinky in your house, have someone hold one end of the slinky and you play with the other end of the slinky. Oscillate that slinky. And if you create reflections that have the same frequency, amplitude, and wavelength, you can get this standing wave pattern. Now the way we describe these standing waves is we have areas where nothing happens. That's what we call a node. Nothing is happening. Those are the areas where the wave is stationary. We have maximum destructive interference here at these nodes. Nothing is occurring. But at these antinodes, that's where the wave is moving the most. Antinode, nothing is happening. The maximum amount of something is happening. And that's where we get these waves really oscillating back and forth. These areas, when it's at its peak, is the areas of maximum constructive interference. That's what these standing waves are all about. These standing waves are really important in music, but we'll talk about that in a little bit. So check out this animation when it resets. We have this string, and we send a wave into the string. Now we learned when this wave hits this fixed boundary, it reflects and it inverts. Now that reflected wave interferes with the incoming wave. That wave is still coming in, and we end up with this standing wave pattern. That's the most common manifestation of standing waves, is this reflection off two ends. We send the wave in, it reflects back, and it starts interfering with the incoming wave. And then you end up with this standing wave pattern. Again, some vocabulary. A wave is a node is a point of destructive interference. That's where nothing is happening on the standing wave. Node is nothing. That would be this point here, this point here, this point here. Any point where you see nothing occurring, that would be a node. And an antinode is a point where maximum constructive interference occurs when it's at its maximum peak. And we can identify the antinodes in this standing wave. Here's one of them. Here's another. Here's another. Here's another. Here's another. Any point where maximum constructive interference occurs. The way I like to identify nodes and antinodes is I kind of draw little circles where the nodes occur. Here's a node, believe it or not. There's a node, there's a node, there's a node. Node, node, right? Node. And then the antinodes will be halfway between each one. I can even draw it before the wave heads in. These dotted lines are where the maximum constructive interference will occur. There they are. Is that magic? Okay. And like I said, standing waves are important when it comes to music. You might have heard this term harmonics before. Harmonics are higher frequencies where these standing waves do occur. So the fundamental, the first harmonic, ends up where we actually have half a wavelength. Now, I might be saying, Mr. Hatzfeld, what do you mean half a wavelength, right? Well, we know that a full wavelength comes up and comes back down. So the full wavelength would be over here. You end up with half a wavelength because we only have a crest and a trough as it vibrates. The first harmonic has these two nodes and one antinode. When you pluck a stringed instrument and you watch it, you'll see that first harmonic because that string will vibrate between its two fixed ends. Another way you could see this is you have a slinky. If you vibrate the slinky at a low frequency, you might be able to catch this first harmonic. If we vibrate it a little quicker, you might be able to see this second harmonic. The second harmonic occurs where we have, where's my marker? 3 nodes. 1, 2, 3, and 2 antinodes. Here we only had 2 nodes. The ends of the wave do count as nodes because nothing is happening on the fixed boundary. The antinode is right in the middle. Here we go. Here we have 3 nodes and 2 antinodes. For the third harmonic, if we vibrate that slinky or that stringed instrument just the right way, we can catch the third harmonic, where we have 1, 2, 3, 4 nodes, 3 antinodes. You might start to see a pattern here. Notice for the first one, we had 2 nodes, 1 antinode. Second, we had 3 nodes, 2 antinodes. Third, we had 4 nodes, 3 antinodes. And these harmonics keep occurring. There's the fourth harmonic. Okay. Now notice how many wavelengths are in each one of these. Here's half a wavelength. Here's a full wavelength, because we come up and we come back down. But for the third harmonic, we end up with 1.5 wavelengths. Fourth is 2 wavelengths. And here on the side, we're just describing how many nodes, how many antinodes, and how many wavelengths occur for each one of these harmonics, these standing wave patterns. Now remember, these standing waves can't occur unless we have the same amplitude, frequency, and wavelength. And they're interfering with one another, moving in opposite directions, creating this standing wave pattern. The standing wave is a manifestation of these 2 waves interfering as they move past one another. All right, so let's try some examples looking at standing waves. We have 2 examples here, one on the left, one on the right. The one on the left, it says, while playing, 2 children create a standing wave in a rope, as shown in the diagram below. A third child participates by jumping the rope. Jump rope is an example of a standing wave. There, it's what we call a torsional wave, because the wave goes around in a circle. It's a standing wave nonetheless. But what is the wavelength of this standing wave? Okay, the total wavelength of this standing wave. So what we see here, we see the first harmonic of this standing wave. First harmonic because I only see 2 nodes and 1 antinode here. Now we said that we need a full wavelength to have a crest and a trough. So how many wavelengths do we really see when we see the first harmonic of a standing wave? Well, all that's shown here is half a wavelength. This 4.3 meters is 1/2 of the wavelength. We'd have to continue it on to see the full wavelength. So if 4.3 is half the wavelength, that means that the total wavelength of the standing wave has to be 8.6 meters. Multiply it by 2. Again, if we look at the first harmonic, the fundamental harmonic, that is only half the wavelength of the wave. To get the full wavelength, we got to take that half wavelength and multiply it by 2. Next, the diagram below represents a standing wave. Here we have our wave generated between these two fixed points. Again, a standing wave is the resultant disturbance of two waves moving past one another. Those waves are still moving, but what it looks like is a single wave oscillating at a single point in space. Really, it's two waves moving across. So we want to know the number of nodes and the number of antinodes shown in this diagram. Well, knowing what they're asking, nodes is where nothing is occurring. Antinodes is anti-nothing, which is the maximum something is occurring. So let's take a look. Let's count where there's no motion in the rope, and let's count where there's maximum motion in the rope. The dotted line is the other location where the wave oscillates back and forth. So counting where we see nothing occurring, I see 1, 2, 3, 4, 5, 6 nodes. So already we can get rid of 1 and 2. We know that there are 6 nodes in this standing wave. But let's see what's going on with the antinodes. The antinodes are the place where we have maximum motion of the resulting displacement. There's 1, 2, 3, 4, 5 antinodes. 6 nodes, 5 antinodes. The correct answer is choice 3. I'm going to erase my TV. Hope you guys are feeling okay with this. As always, shoot me a message if you have any questions. By understanding how these general waves work, we can better understand how all the different waves in nature work. And one more thing I want to discuss for this video is something called two-source interference. Now this is complicated, so let's work it out. Two-source interference. When we have two things creating a wave, those are our two sources. And the waves from those two sources are going to interfere constructively and destructively. What we're looking at for these both the animation and the diagram is kind of like a top-down view of the two sources of a wave. The type of wave it could be a sound wave, it could be a water wave, it could be a lot of different types of waves. But what happens is, here's S1, here's S2. Let's start it over. They're creating the wave, and you're going to see the wave fronts emanate from the points of these waves. There they go. There's those wave fronts. And wherever the wave fronts overlap, we could look to see whether it's constructive interference or destructive interference. Where we have a bold line, we have crests of the wave. Crests are the upper portion of the wave. And where we have thin lines, we have troughs of the wave, the lower portion of the wave. Well, when we have two crests interfering, we're going to end up with constructive interference. And when we have two troughs overlapping, we're also going to end up with constructive interference. The two troughs and two crests are going to have a greater resulting amplitude. These red dots are the antinodal lines. You don't really have to know that, but it's all the points in this two-source interference where we end up with constructive interference. If you look at the diagram, it's static. We can see these green dots are the locations of the source. And look at these thinner lines. These thinner lines are two troughs, so we end up with constructive interference there. These thick lines are the crests, and when they overlap, you end up with constructive interference. Again, two troughs, constructive interference, two crests, constructive interference. But when we have a crest and a trough overlapping, that's the blue lines, that would be destructive interference. Okay? Again, we're looking at the wave fronts of these two sources. Thick lines are crests, thin lines are troughs. And if you can just identify either a place where you have two crests or two troughs has to be constructive, and then a place where you have a crest and a trough would be destructive. The really cool thing about two-source interference is if I set up two speakers, if you set up two speakers in your room and both those speakers are playing the same tone, you can actually walk on the other end of the room along the wall and you'll hear places where it's super loud. That would be the constructive interference. and you'll hear places where it's super quiet. They'll be the destructive interference. And those are the places, so the maximum constructive is where it's two crests or two troughs, and then the maximum destructive is where it's a crest and a trough. Those two sources will interfere with one another. You could actually see this with water waves as well. If these two sources were creating water waves, you'll see places where we get maximum constructive interference and maximum destructive interference. All right, take a look at this video. This is an example of two-source interference for a water tank. We can actually see the waves move along the water. MIT Physics Group has some great physics demonstrations on YouTube. Okay. So what they're doing is they're creating this interference pattern in the water here, and they're projecting it on the wall. Here's the 2 point sources in the water. Changing the frequency of oscillation. There it goes. Now it's kind of hard to see in the water, but look at the projection. The light comes down and projects it on the screen. There it is. Now you can see the places where you have constructive interference. And you can see the places where you have destructive interference. The destructive interference are these lines here where you see nothing really occurring. And then the constructive interference occurs here, where you can really see the waves ripple there. And again, you could experience this with sound. If you create 2 point sources of sound, you can hear places where it's loud, constructive interference, or places where it's quiet, destructive interference. So let's try an example of this two-source interference. Here's what's going on here. We have two speakers, S1, speaker 1, and S2, speaker 2. They're operating in phase in the same medium, producing the circular wave pattern shown in the diagram below. Okay, now based on the diagram, always take a second. I know these diagrams look really complicated at first. Take a step back, look for a key. Look for some way to make sense of this diagram. The bold lines are the crests of the wave. The dotted lines are the troughs of the wave. So this speaker is producing these crests here. And the troughs here, the dotted line. So basically what it looks like coming off speaker 1 is crest, trough, crest, trough. Same thing with speaker 2. These speakers are creating the same pitch. We can see that they're operating at the same frequency. And what we want to know, at which 2 points is constructive interference occurring? Now, where does constructive interference occur? It occurs at 2 places where we have either 2 crests or 2 troughs. Having both of those, either both crests is going to make a higher crest, or both troughs is going to make a lower trough. So let's take a look. We have points A, B, C, and D, the 2 points where we're going to get maximum constructive interference, well, we have point A. Here are 2 troughs. Those 2 troughs are going to add to create an even greater trough. That would be a point of constructive interference, building a greater thing. And point D is going to be a point of maximum, also a point of maximum constructive interference. Those 2 crests are going to add to create a even greater crest. So the correct answer is points A and D. Option 2. Points B and C. We have a crest and a trough. Those are going to destructively interfere, canceling each other out. Along with, and same thing with point C. We have a crest and a trough interfering, canceling one another out. Okay. So that is it for this video. Hope I wasn't moving too quickly. Next thing I want to do is I want to discuss how these particular ideas affect music and what's the difference between music and noise. That'll be the next video that I'll be posting. Okay, well, hope everyone's doing well, and I'll see you in the next video.